Leetcode 300, longest increasing subsequence. Very famous problem and also very deceivingly hard. So here it's classified as medium, as you can see, but I often disagree with those classifications from Leetcode, since most of the time I think they are based only on the final code for the most optimal solution, and they just check how long it is, how complex it is, and if it's very long and complex, then they classify the problem as hard. But if it's short, let's say, then it's easy, and somewhere in between is medium. No one knows where it starts and where it ends. Yeah, but oftentimes, of course, the final code is the easiest part, yeah, if you know what strategy to apply. And the hard part is actual thinking about this problem and trying to compare various algorithms that you can use, various data structure, and choosing the one that is the most optimal. Yeah, and just coding is the final 5 minutes maybe, or final 2 minutes out of, let's say, half an hour of thinking. And that's why I disagree with that. And here in this particular case, of course, the most optimal solution is not that hard to code. It's just a for loop with if statement inside. But the hard part and the interesting part is how can we arrive at that strategy. So here is the description, and we will try to explain everything as detailed as possible. And let's just start from the very beginning. Given an integer array nums, yeah, so that's the input. We have an integer array, linear data structure with or linear container with some elements inside, and all of those elements are numbers, integers, and they can be, here below you have some constraint, both negative and positive. Yeah? So sometimes it's just positive numbers. Sometimes the numbers have to be unique. In this case, they don't have to be unique. It's just integer array. And so there can be repetitions, and it could be both negative and positive integers. And the next thing is our task. So we have to return the length of the longest strictly increasing subsequence. And in this sentence, every single word carries a lot of meaning, and we have to first of all understand what does it imply, and then use that knowledge for our algorithm. And the first thing is that we have to return the length, yeah? Meaning we have to return just a number. And if you look at the right side, the type hint for the Python solution is int as well. And that usually, and here as well, implies that the solution is slightly easier than otherwise. If, for example, we had to remember the subsequence itself, then we would have to store it probably in some additional structure. But in this case, we don't have to keep the whole subsequence. We just have to keep track of the length of that subsequence, and which might simplify our final algorithm. And the next thing is that this length represents the longest strictly increasing subsequence. Yeah, longest meaning that we want to have the longest possible, as many elements as possible, such that we will have strictly increasing subsequence. And strictly increasing means that there cannot be any repetitions. So in the input array, we can have some numbers repeated multiple times, but in the output, in this strictly increasing subsequence, we only take each number once, yeah, at most. And increasing, of course, means that first we have smaller numbers than the larger numbers, and subsequence is one of those types of substructures from arrays, which are very common in various Leetcode-like problems. There are subarrays, subsets, subsequences, permutations, and combinations, and all of them carry different meaning and hint at different data structures and algorithms. And today we are discussing about subsequences. So what is a subsequence? A subsequence is an array that can be derived from another array by deleting some or no elements without changing the order of the remaining elements. Meaning, let's take a look here at the first example, and we have some array, And for subsequence, I can simply take first element, then skip couple elements and take the next and the next and so on. And that's how I can build different subsequences. I can either take an element or skip an element, but I cannot change their order. Yeah, in the subset, I can change order, and in subarray, I cannot skip any elements. If I just create a subarray, I have to take all the elements the way they are. I cannot remove anything. And in subsequence, I can. So it's just one of those substructures which we have to understand what they imply. And since we are already here in the first example, let's try to understand what do they expect from us. And we have the following array: 10, 9, 2, 5, 3, 7, 101, and 18. And the output is 4. That's because the longest increasing subsequence is 2, then 3, then 7, then 101. And therefore the length is 4. And as you can see, they skipped 5, because that's allowed in subsequence, and all the numbers are strictly increasing. And they could also choose another subsequence, 2, 3, 7, and 18, because there can be many subsequences of the same length. And we don't care about the subsequence itself, we only care about the length of the longest, and that's important to remember. And the second example is 0, 1, 0, 3, 2, and 3. And here also the output is 4 because we can take 0, 1, 2, and 3. And that's longest subsequence. And the last example, we have 7 repeated multiple times. As we said, we can have repetitions in the input array, but not in the output subsequence. That's why the longest has just a single element, because all other are repeated. And we cannot repeat in the output. Okay, so let's copy that, and we will think about it in greater detail. And let's copy this as well. Maybe a bit smaller, too big, like this. And our task is to find a subsequence. In order to construct a subsequence, for each element, we have two options. We can either include or exclude. That means that how many possible subsequences we have. For the first element, we have two options. Then for the second element, we have two options. Then for the third element, and so on up until n. We can do it n times if there are n elements. Which means that, let's make it a bit bigger. We have 2 to the n options, which is exponential complexity, which usually we don't like. We want to solve always all the problems in the most efficient way, and the best option is always logarithmic, then linear times logarithmic, then square, and so on. And the exponential is somewhere very far away. We don't like it, and we also don't like factorial complexity at all. So always we try to have either logarithmic or linear at best, or some combination of those. And that's it about the possible subsequences. So of course, this means that we will try not to generate all the possible subsequences, but how else can we solve it? Well, we can observe that each subsequence or subsequences of the same length are dominated by subsequence of smallest tail. Yeah, and the tail is the last element. And why is it so? Because order matters. Yeah, and when we find a subsequence of the same length, since we cannot just reorder them and find the smallest possible tail, that means that there won't be any subsequence better than that, because we cannot just reorder the elements. If we already take the smallest element, that is the best option we have. Let's make it like this. Okay. And let's put it here. What do we mean by tail? This is the last element. Yeah, and we'll of course show it on an example, but just at the very beginning, let's make it clear that that is our strategy, and we'll try to prove it. Why is it so? Or here with the smallest tail, maybe that's better. Let's add a here. Yeah, but generally we will be gathering the tails instead of the subsequences. Yeah, so let's move that as well. And the structure where we will be storing those tails, we will call it tails. Yeah, so that's the most important part. And now is the algorithm. So for each element, let's call it num or x in nums, we will do the following. Yeah, as you can see, it's for each element, meaning that we will iterate, and meaning that we already have n complexity. Yeah, so it's at least linear, but of course there will be something happening here inside, so it will be a bit slower than linear, but how slow we will see in a second. We will try to find the leftmost I such that nums or the nums on index I are, no, sorry, not in the nums, but in the tails. Here we will be storing our output. So we get the numbers, the elements from nums, and maybe let's call it num, not x, not to introduce too many strange letters. Yeah, and inside the tails, we will try to find the leftmost I, the index, such that tails of I is greater than or equal to our number. And to do that, we can use bisection search, which has O log n complexity, time complexity, of course. And then we have two options. If no such I exists, then append num to tails, yeah, and else update tails on that position with the value of num. Yeah, and we'll use it this algorithm here in a second for that example and see how it works in practice. But first, let us write it down. So here we have, of course, this happens for each element num in nums, meaning that here we will have on. Yeah, so the whole the complexity of all of that would be O(n) times log n. Yeah, so linear times logarithmic instead of exponential. Yeah, so that's the final complexity. And we'll explain in a second how bisection search works. And that's more or less it. I'm just verifying. Maybe let's also put the same variables, highlight them in the same way. So we see that that's the I that we will be trying to get from bisection search. Then here is I as well. And the number comes from here, from the input. Then we use it here, here, and here. Yeah, and of course we have tails as well. Here's tails, here's tails, and here's tails. And inside, in Python, we have two built-in functionalities for bisection: bisect left and bisect right, which both of them return an index. And this one returns I such that A on the index I is greater than or equal to some X. And of course, that where A is our array. And right returns let's separate this such that A on the index I is greater than, so not greater or equal, but greater than X or X rather. And let's see an example. So let's see, we have following array, 1, and then 3, 3, 3, and 5, or 6, and 9. Let's say something like this. And 3 is repeated 3 times. And let's say that our X equals to 3. Yeah. Then bisect left will return this index, and bisect right will return this index. Or bisect left, and I equal to 0, 1, 2, 3, 4. And from our bisection search, since we will have no repetitions in tails, we will use, of course, bisect left. So now let's move that one here and try to run that algorithm inside Excel Draw with our beautiful animations and graphical effects, and see how it works in practice. So besides the nums, we will have, of course, tails, which will initialize to an empty list. So that's the initial stage. And now let's create following columns. So we will be iterating through nums, choosing a num, Then we will be trying to find I using bisect left. And then we will be updating tails. Yeah, so let's start like this. And the first number is, of course, 10. Yeah. The I uses bisect left for x equal to 10 in this array, which is empty, which of course returns 0 at the beginning. And there is no other option. We have no other place. And the tails, of course, after this operation looks like this. And then the second is 9. I is equal to 0. And then we update like this, since again no such I exists, that tails of I is greater or equal to the num, and we have smaller numbers, so we have to update on index I. Then 2, which is again the same thing, and no such I exists, and then 5 will be the first, which is greater than, and every element here, which will return the I after that, meaning 1. Yeah. And here the next one is 3. Yeah, I will still be 1, since 3 is better than 5. Like this. Then the next one is 7. And 7 is bigger than all our current options. Let's make it a bit longer. So we will have 2, 3, and 7. And the index will be 2. And we have 101 and 18. The last two. 101. Index is 7. No, sorry. Index will be 3. Because it's greater than all of it here. Yeah, and 18. Like this. Yeah, and now the length of this is what? 4. And that's our final answer. And so important information on any index I at any point. The best possible subsequence, this is the tail for the best possible subsequence of length I plus 1. Yeah, so at any point we will have best possible tail on any point on index I, maybe like this. On index I, have best possible tail for a subsequence of length I plus 1. And why is it so? Because this we will always, when we find a better tail, we'll update it. And because we cannot change order for those subsequences, that means that we will never have a possible option of having a longer subsequence than the one that we have right now. And if we find that no such I exists, so meaning that this one will return index greater than the length, then we will append, and that means that we have found possibly a longer subsequence, and that's how we will be updating. And that's it. We just need to translate it to Python, which should be simple. So for number in numbers, the index is bisect left from tails. And we have to initialize tails to an empty list, and the x is called num here. And now if I is equal to the length of tails, then we append. Otherwise, we update. And we return the length of tails. And of course, that solution in itself is very simple to code, but to understand where it comes from and to be able to recreate it, let's say, in an interview scenario, you have to have some additional information and understand what's going on. Now let's run first for the 3 initial cases to see if everything is okay. And since it's okay, we can submit for all the cases and see how we did. We beat 84%. We try again. Maybe it will get better, maybe worse. Let's see. Yeah, we beat 95% with that solution.